Hello, this is Summer 2019, question 4, combination. So I think I'll just do part A in this video. Let's go ahead and read the definition. So a combo of a non-negative integer n is the result of adding or multiplying the digits of n from left to right, starting with 0. So for example, for n equals 357, a possible combo, you can get a possible combo by doing 0 plus 3, plus 5, and plus 7 to get 15. Another possible combo is 0 times 3 plus 5 times 7. That would be 35. And maybe one more would be if we just change this multiplication sign to a plus sign. So that would be 0 plus 5 plus 7, 12. And all of those are listed here. There's also an example for 36, which is not a combo of 357. And that's because of the way these parentheses combine. So in order to form a successful combo, you have to start with 0, combine it with 3 using either addition or multiplication, and then combine that whole quantity with 5 using either addition or multiplication, and then combine that whole quantity with 7. So that's why 36 is not a valid combo. Our first question is to implement isCombo, which takes non-negative integers n and k and returns whether k is a combo of n. So for example, isCombo of 357 and 15 should return true. So we're returning a Boolean value here, but 357 and 16 would likely return false. And you can see in the dog test, they basically use a list comprehension to get all the combos that are in the range 1000. So anything from 0 to 999 that is a combo of 357. So in this case, the first thing we can observe is that at every step, for every digit, we have a choice. We can choose to either multiply or add a digit. And because we have that choice, and we're sort of going to be simulating all these possibilities, this is going to be a tree recursion problem. And you can also see that by just looking at the examples or the recursive calls here, where you have one recursive call to isCombo in the added variable, and then one recursive call in the multiplied variable. And in the end, you combine these two recursive calls to get added or multiplied. Let's first just try to figure out what the recursive calls will be. So they gave us a bit of a hint. Either you're adding or you're multiplying. And the key thing with these recursive calls is that we have to figure out how to make our input to the problem smaller and closer to the base case, right? So for example, if we had 357 and 15, or let's use one that has addition and multiplication, so 35, then 35 we know is 0 times 3 plus 5 times 7. And we somehow want to split this up into two possible cases. So maybe on the left we'll do the addition case, and on the right we'll do the multiplication case. The interesting thing here is that we're not exactly building up or choosing a number to add or multiply. We're not oh, take k and then either add 7 to it or multiply it by 7. We're actually going to be doing the opposite, because we're checking if 35 is a valid combination of 357, which means can 35 be formed by adding and multiplying 3, 5, and 7, just like we've done on the right. And in order to figure that out, to simulate addition or to simulate multiplication, we actually have to do the opposite. So we can simulate the fact that a 7 was used. Either it was multiplied or it was added. So somehow we have to reduce this 357 to 35 because we're using the last digit. And we have to figure out what the opposite of using that last digit is to to our k, which is 35. Well, the opposite of addition, that's just subtraction. So if the last operation that was done was that a 7 was added, then we can just subtract the 7 to get 28 and see if the rest of that 28 can be formed using the numbers 3 and 5. And this is actually not possible, so this will end up eventually returning false. On the right side, we pretend like 7 was just multiplied. So we could pretend to do 357, but we get rid of the last digit, so 35, and divide this 35 by 7. Division is the opposite of multiplication. So we get 5 here. And in this case, this would eventually actually return true, because in the valid combination, 7 was in fact used. It was multiplied. And if we divide both sides by 7 here, then we get the remaining combination, which is 0 times 3 plus 5 is equal to 28. So this subproblem, oh sorry, that's not 28, that's 5, sorry. This subproblem is also solved, and we can continue to simulate it using our addition and multiplication. So addition and multiplication. Let's go down addition because we know that's correct. So to simulate using the 5, we cut the number down to just 3, so we remove the last digit. And to what do we do to 5? Well, we just subtract out the number that was last added. So we just get rid of this and then get 0 on both sides. Finally, we have to simulate using this 3. So either addition or multiplication. In this case, we know the answer is once again multiplication, but the addition case would end up returning false somehow. So for multiplication, the opposite is division. So we do 0 divided by 3, and we use up this 3, so we do 3 floor div 10, and we get 0, 0. In this case, we've traced this valid sequence of operations where we take 0, we multiply it by 3, we add 5 to it, and then we multiply 7. That's exactly what our path is. And in this case, we want to return true, since it is possible. And we can figure out what gives that away. But since we've sort of figured out what the recursive cases are, let's fill them out. So we always said that we want to be doing n floor div 10 to get rid of the last digit, to simulate using it. And they've stored that in this variable rest for us. And then what do we want to do to k? Well, we want to take what k was and then reverse whatever operation we think could have been done to it last. So we take k. In the added case, we just subtract out the last digit. So in the very top case, we just subtracted out the 7. And in the other case, we just divide out by 7. Now there's a couple conditions that need to be true for us to actually be able to do this, to make these recursive calls. In the case of division, well, we know that if division was what happened, then we're going to get back an integer when we do k divided by last. If we get a decimal somewhere, well, you can't make decimals by just multiplying together whole numbers or adding. So that would not be possible. So we actually have to make sure that k was divisible by last. For the other case, the addition case, we can go back to this assert statement at the top here that ensures that we have a positive n and a positive k, which means that the inputs to combo have to be or positive or non-negative, really. And for that to be true, well, k has to be greater than or equal to last. If you ever go into a negative input, then your answer is false anyway. So this basically says if k is not greater than or equal to last, then the added case is not a possibility. Now all we have to do is figure out our base cases, and for that we can take a look at this 0, 0 here. So in the case of 0, 0, we do want to return true. Now what is it that's giving us this indication? Is it n or k? Well, let's think about what n represents. N represents the digits that we're using to make the combination, and k represents the combination that we're making, right? If n goes to 0, well, that just means that we've simulated using all of the digits. But if n was 0 and like k was, say, like 5, then we don't want to return true because we've used all of the digits, but we haven't made the appropriate k. On the other hand, if k is 0, that means you've successfully done addition and division to make the original number. So to make 35, if you can say maybe like subtract 7, divide it by 4, and then subtract 7 again, then you've done a series of division and subtraction that, when reversed, will make up 35. So namely, like 7 times 4 plus 7 would make up 35. So once you reach k equals 0, then you're done. Then you return true. I also kind of alluded to the other base case. If you reach n equals 0, but k is not equal to 0, so if you've used up all your digits, but you still haven't made up the number that you were trying to make, then you've taken an incorrect series of steps. So that's pretty much it for this problem. A couple key takeaways that I might remember. The way we identified that this was a tree recursion problem was we saw that there were a bunch of choices that we had to make. The way we figured out what our like recursive cases were, we said that our number has to, n, has to be smaller every time because we're really simulating using a digit of that n, and trying to break this problem down into a smaller case. Very often when you're working with numbers, that would be like n goes to n florative 10. If you had a similar problem with lists, then you might take like a slice of that list, or you somehow might make that list smaller. Finally, at the end, we combined both of these choices by using an OR statement in this case, because we were trying to see if there is one valid possibility. That means whether we add or multiply, it doesn't matter. As long as one of them returns true, then we also want to return true. You can also combine things differently. For example, if you're counting a total number of things, then you'd be adding, right? But in this case, we're working with Booleans, so we use an OR statement. Lastly, for the base cases, you might not have the patience to or the time really, to draw this entire tree out and figure out how things work. So the first thing I would really do is consider your inputs n and k and see like what values of them like you know the answer for. So for example, like we know that like when we have k equals 0, then we've really finished forming the number. We've reduced the number down all the way to 0 by doing some sort of series of operations. So that's how you might think about the base cases. You can just think about simple inputs to the problem. And then if you're stuck and if you have the time, maybe trace down some examples like we did in the tree here. Other than that, I'll be back in the next video with parts B and C.